Hi! Well, we've got to the final module, and I promised in the introduction that I would show you the timer that I designed. And if you look in the description text down there, you'll find links to both the schematic and to the source code. So let's have a look at the schematic first. The schematic is pretty simple. This part inside the dotted line here is the power supply. It uses a capacitive type power supply, but I haven't supplied the values of these components because I don't know whether you'll be designing it for 50 Hertz or 60 Hertz or 110 volts or 240 volts, and these component values depend on those things. There is a link above it there to tell you where to find it all, and he gives you all the design criteria to design those components. As for the rest of it, this is the actual circuit. It's pretty simple. There's the ATtiny chip that drives a couple of LEDs for timer mode and programming mode on port B3 and B4. There's the button is on interrupt 0. I'll come to that in just a moment. On port B1, we've got a transistor driving the relay. I could possibly have taken this lead just directly to the relay, but I thought that it might be overstressing the chip a bit, so I decided to take that through a transistor. I think it's safer. And apart from that, there's the little beeper unit, and that's just directly connected on PB0. Int 0, interrupt 0, all of the pins on the chip are multi-purpose. So there's port B0 and port B1, for example, carry MISO and MOSI, which are the signals used for the two-wire interface for serial communication. If you were going to connect a crystal to this chip, then the crystal there goes between these two pins. This pin here is normally port B2, and I've configured that as an input because the button is connected to it. But when the chip finishes its timing session, it switches off the relay and the LED and it goes to sleep. And one of the things that can wake it up from sleep is interrupt 0. So before it goes to sleep, I configure that pin as interrupt 0 so that I can wake it up again. Then when it does wake up, that interrupt routine that looks at interrupt 0 sets this port back to port B2 so that it's an input for the button. Okay, I don't think there's too much more to say about the schematic. So let's have a look at the program. One button timer. There it is. At the top of the code, if you want to know how it works, there's copious notes as you see. I suggest you go through those. There's a lot of good information in them. It might be worth making a copy of the registers. Control C to copy, and just put them into a separate editor to the side so that you can just flick backwards and forwards to them for reference. I'd like to point out the disclaimer on slide 0. It just points out that the program is not perfect. If you go through it with a fine-tooth comb, you will find errors. You'll find comments that are misleading sometimes, and you'll find the odd place where things were put into the program because they seemed like a good idea at the time, and then later on they weren't such a good idea and are moved on and they just got left in the program. So they're still there. They don't actually do anything, or they don't do anything harmful in any case. And there's a little example there at the bottom of that screen where the program was not as efficient as it might have been. It could have been rearranged to be a bit better. Right, now if you go to slide 1, it's a little explanation of the end of the timing sequence. There it is in the program. From this label here, finished, and it's just how the chip gets shut down at the end of the session. I'd just like to draw your attention to these two instructions here, which switch off the relay and the LED that is still alight. I was quite surprised to see that when I put the chip to sleep, there's the sleep instruction there. When I put this chip to sleep, the LED was still on, and the sleep mode is called power down, so I assumed that it would power down the chip, but it doesn't. Any ports that are left high when you put it to sleep stay high, so be aware of that. The reason why I wanted to look at the sleep first was because the next thing we're going to come to is the interrupt zero handler, and this is what wakes it up again. Over here you see we enabled the interrupt zero interrupt. Well, that's what wakes it up when it gets an interrupt when you press the button. So it disables sleep mode. Chip gets wakened up by a button press. So wait for the button to be released again, because remember that it's timing this on a millisecond basis. So you put your finger on the button and it's going to take it quite a few milliseconds before your finger comes off the button again. So it waits in the interrupt routine until the button is cleared again. And then it jumps out to main to reinitialize all the functions of the timer, and by default it goes into timing mode. In the program, the interrupt zero handler is right up near the top of the program at line 173. The explanation of what it's doing is here on this slide. And the next handler we come to is the compare handler. This is the timer compare. There are only 3 vectors in the vector table. There's the main reset vector, which is actioned when you switch the chip on. There is the interrupt zero handler, which gets used to wake the chip up. And there is the main timer compare handler, which is the interrupt that looks after our timers. The main timer handles a number of timers for us. The first one is the one that sends a flag to the idle loop every millisecond. When we were doing this in the tutorial, I divided the CPU clock by 8 and then set the output compare register to 125 so as it would count up to that limit in 1 millisecond. However, when I was writing this, I had not yet had that good idea, so I worked around it another way. This one runs at CPU clock speed, so it runs at 1 megahertz, and the output compare register A is set to 249, so it gets there in a quarter of a millisecond. So R3 is initialized to 4, and it counts down 4 quarter milliseconds to give me the 1 millisecond flag. It maintains a button timer for us in R8, R9. The button timer can be stopped by setting R23 bit 3, but if that's not stopped, the button timer is allowed to run. It can also be reset by register 23 bit 2, and if it is reset, then it's cleared and it starts counting from 0, and it simply counts up in these 2 registers. Then there's a beep timer. The program can load a value into R20 and start the beep beeping by raising its pin, which is port B0. Then it raises R22 bit 3, which is the beeping bit, and as long as that is set, the interrupt timer here, it'll count R20 down to 0, and when it gets down to 0, it'll turn the beeper off. There's a quarter second counter, which simply counts 250 milliseconds, so it counts from 250 down to 0, and at the end it sets a flag to say that the quarter second has expired, register 22 bit 1. And then there's a 1 second timer, and that is the timer that is used by the actual timer routine when it's in timing mode. It counts the number of seconds. So that counts down 4 quarter seconds, and when it gets down to 0, it sets R22 bit 3 as a flag to say that 1 second has expired. Main is pretty much a repeat of what we saw in the tutorials. Set the stack pointer, set all of the interrupts and the necessary registers, the variables. There's one extra thing that I do. I set a 0 into R0, I set a 1 into R1, and I set FF, or -1 if you like, into R2 to be used as constants throughout the program. I just find it handy to do that. You can't get much simpler than the idle loop. It checks every millisecond to see whether the end of the millisecond has been flagged. If it hasn't, it goes back and waits some more. If it has, it checks the mode that it should be in by looking at register 21, bits 2, 1 and 0. The modes that it can be in are timer mode, programming mode or replay mode, and each one of these is set by putting a bit in the relevant flag. And when it's decided which mode it should be in, it jumps there. There's the idle loop in the code. There's where it's waiting for the flag to be set, and it jumps back to idle and checks again to see if the flag has been set. When it has been set, this instruction here fails. It comes through, it then clears the bit, and it checks R21 to see which mode it's in and jumps to the relevant place. Timer is the default setting, and it is set by default by this instruction here at the end of main to set timer mode. From timer mode, you can set it into program mode, and at the end of program mode, when the programming is completed, it then jumps automatically to replay mode, where it replays the program that you've entered for confirmation. Timer mode is fairly simple. It retrieves the value from flash memory that was programmed in by the program section. It puts that value into R18 and R19. It bips to indicate that the program has started, and then it simply counts down those two registers until they get down to 0. When they do, it beeps again to let you know that the timer has finished, and it switches off the relay. During the time that it's in its timer loop, it also checks the button to see if you want the timer to be cancelled. The timer section starts at line 794, and it's all really simple programming. You can just read through it. The programming mode starts simply enough. There's just two little statements in the program loop to check the button status and to call the button timer, and it runs around this loop, remember, every millisecond. When it's checking the button status, it checks to see if the button is up or down, which it does by looking at, it says here, by checking the flags. It does that by looking at the input port, the pin that the button is connected to. Then it checks to see if the button is up or down and debounced, and the debounce mechanism is on the next slide, slide 6. So let's just look at that first of all in the code. Here's the program loop. So it calls button status, and then when that comes back, it calls button timer. Here's button status here, and it checks the input pin to see what the state of the button is. If it's down, it jumps to button down. If it's up, it just comes here. I've put a label in there, not because there's anything that jumps to it, but just because it marks it in the program. It makes it easier for me to read it. Let's look first at the case where the button is down, because the button is up initially. So if the button goes down, SEC is set carry, and it rotates that left into register 4. Then it looks to see if register 4 is a fox. If it is, then the button is down and debounced. Let's just look at that again on the slide. So here's initially register 4 looks like this. It's all empty and the carry bit is 0. If you see that the button is down, you set the carry bit and you rotate it into register 4. Every time you see that the button is down, every millisecond that the button is down, you set the carry bit and you rotate it into register 4. And the way that rotate works, it's like this arrow here. It gets rotated all along register 4. Whatever is in the top bit there comes out and it goes back into carry. So that every time this happens, the carry in fact gets reset to 0. but we explicitly set it every time. So that's how it works. Now, this just shows a button bounce. So for 1 millisecond that you look at it, the button is up. So you clear carry and you rotate that in. But then the next time the button is down again, so you set carry and you rotate that in, you set carry, rotate it in, and you can see what happens to the register here. And finally, all of the bits of the registers are all ones, so the register is Fox Fox, and at that point it decides the button has been down for 8 consecutive milliseconds, it's debounced. If the button was up, then you clear carry each time and you rotate that in, and when the register is finally all zeros, then the button is declared up and debounced. And whether it's down and debounced or up and debounced, there is a flag that it sets to state that, so that it can check the flag later on. Now, having decided whether it's up or down and debounced, it then decides whether it is newly up or down and debounced. So button newly up and button newly down. And it does that by checking the flags, and you can see here the flags that it's checking. Here's our registers. There's 23. Here's button status is up or down. Button status debounced is a 1. If it's not a 1, then you consider that it's still bouncing, or that the register has not completely filled yet. And whether the button is newly up or newly down, we set register 23 bit 2, which has a value of 4, to tell the interrupt routine to clear the button timer, and so that when the button is either newly up or newly down, the button timer starts counting from 0. So from that moment, it starts counting to see how long the button has been down, and we'll be seeing that in just a moment. So if the button is newly up and debounced, the first thing it does is it flags up status, so that next time it comes around in the next millisecond, it will find that the button is already up, so it won't think that it's newly up. However, if it is newly up, it flags the up status, it flags the interrupt service routine to clear the button timer so that it starts counting from 0. It enables only T2 and T4 bips, we'll see that in just a moment, and waits for the end of the millisecond to ensure that the IRS, that should say ISR, has been visited and that the button timer has been cleared. Similarly, if the button is down, it runs through these instructions. So those instructions are these button newly up, and it's these instructions, and these if it's newly down. Once it's done that, there's a return instruction, and it goes back to the section here. So it's now checked button status. If it finds that the button is debounced, register 23 bit 1, then it falls through and it goes to call the button timer. Button timer is down here. You see that the button timer is divided into a number of modules which all start with a label T6, T5, T4, etc. And these are times. In each module, it loads R17 and R16 with a number, in this case 1388, and 1388, OX 1388, or hex 1388 is 5 seconds. So it checks to see if the timer has reached 5 seconds, and it does that by calling this CP word, compare word, which is a subroutine that just compares R17, R16 with the timer registers. And if it is less than that, then it says branch on less than to T5, and it comes down here and it says, oh, well, it wasn't 5 seconds yet. Is it maybe 2 seconds? And it does exactly the same thing. It calls the compare word. It does a branch on less than to T4. So it runs down these pretty quickly until it gets to the position where it is not less than. It's actually more than that value, and then it executes the instructions in that routine. If we look at the slides again, here we see that timer routine. So here's T6, T5, T4, T3, and for each one it comes to, it checks to see whether it has reached that amount of time yet. If it has, it does some actions here. If it hasn't, it drops through to the next one. So let's just look at the previous slide. Now this is a bit complicated. This shows time running along here, and it gives an illustration of entering a 2 and an illustration of entering a 0. If you enter a 2, it starts with the button up initially. Now you've just gone into programming mode. You're probably thinking about what you're going to do, what numbers you're going to enter, and sort of mentally preparing yourself to start entering the numbers. So during that time, you don't want the button timer running, because as long as the button timer is running, it's kind of forcing you to be doing things. So you clear the button timer first of all, you switch it off. R5 is the register that counts the number of times you have pressed. So if you're going to press a 3, press, then that counts 1, 2, 3 in register 5. So wait until the end of the millisecond to allow the interrupt service routine to clear and stop the timer. Now, from the button up position, we press button down, button up, button down, button up. It can only actually recognize what the button down was doing when the button comes up again. So this is time 0 down here. This is 250 milliseconds time down here, 500 milliseconds time. If you enter a 0, you press and hold the button. So you press the button at 250 milliseconds, it goes bip, but you don't release it. You continue to hold it, then at 500 milliseconds it goes bip, and at that point it knows that you've entered a 0. When the button comes up again, it stores R6 and R5 into memory. R6 is the number of numbers, R5 is the number that you've just pressed. If you've just entered a 0, R5 will be set to a 0, and R6 will increment to say that you entered a number. The number of numbers is stored in location 100 in memory, and the other numbers are stored in locations 101, 102, 103, etc. Remember that memory is full of zeros by default. So you might be entering a 300, or you might be entering a 3000. This is the number of seconds that the timer is going to time for. So it needs to know how many numbers you've entered, whether 300, 300 is 3 numbers, and it will know that it's only got to interpret 3 numbers to find the time. If you entered 3000, then it has to know that you entered 4 numbers, and consequently you need to interpret 4000 to turn that into a binary number to store in memory for the timer to count down. If you haven't entered a 0, however, you're entering a 2, so you press the button down, the timer starts. It bips to indicate that you have entered well, I call it a digit. It's a press really, because remember there's several presses in a number. So it bips to indicate that you have entered a press. And at that point, it could bip again, because you could be entering a 0, but a 0 for the very first character is invalid. If you're entering 32 seconds, then you could enter 032, you could enter 00032, but the leading zeros get ignored. So you could bip on that first one, but it would be invalid. However, we hope that you have released the button before that, so it does in fact count a digit, it counts a press, and at that point it blocks the T3 bip. Now over here it bips on T2 and it bips again on T3, but this is the first character you've pressed, so it's going to be at least a 1, it's not going to be a 0, so from here on we block the T3 bip. Then you let the button up again, so there's the T3 bip is blocked. You let the button up again, it increments R5 to say that you have made a press. Then the button goes down again, it bips again at 250 milliseconds. The next one it won't bip at, even if you do accidentally hold the button a little bit too long, because that bip has been suppressed now. However, it will increment R5. As soon as you let button up, there it's increments R5. It knows that you have entered a 1 because the timer routine tells it that. We'll see that in a moment. So when you let it up again, it increments R5, disables T3. It does that by default every time now. And at T4, which is 1 second, if the button is still up, it stores R6, which is the number of numbers, which at this point will be 1, and it stores R5, which is the number of presses. So you've entered a 2. If you have finished entering numbers, the button will stay up for longer, and when it gets up to 5 seconds, that's the point where it senses that you have finished entering the number sequence. So if you're entering 946, then you wait long enough for this to reach 5 seconds, and at that point it goes in and it says, oh, there's a 9 and a 4 and a 6, and it interprets that into a binary number which it stores in memory. So it does all of that by waiting for the requisite time period, so in other words T2, T3, until it gets to that time period, and then it performs the actions that are in that module. So for example, it has decided that the time is less than T5, it comes down to T4, the time is less than T4, or if the time is T4, then it will go through all of the instructions in this module here down to the return. There's the label here, store result. So if it does a branch not equals on this operation down to store result, then it'll store the result into memory. And here you can see the X register, which points to the RAM at location 100, and those are the instructions that store it into memory. T2 is also quite a big one. There's quite a lot to do on T2, and if it's less than T2, it falls through to T1, which is less than 250 milliseconds, and if the button hasn't been down or up for 250 milliseconds yet, nothing happens, it simply returns. There's the BIP. It sets R20 to 15 because a BIP is only 15 milliseconds long. It sets port B0, which is tied to the beeper, so it starts beeping at that point, and then it sets a flag bit to flag the interrupt service routine to start counting down the 15 milliseconds that you have set into R20, and that's all handled by the interrupt service routine, so you don't need to look at this again. The program can go off and do other things. Similarly, the beep is exactly the same, except you set 200 milliseconds in, so the beeper sounds for longer. Here's the compare word subroutine that we saw. This every time it comes up with a time, it sets a time into R17 and R16 and calls compare word. Compare word. It switches off the interrupts because I didn't want to compare the first word and then it gets called off to an interrupt and something gets changed. I just wanted to avoid that scenario. So it's only 2 instructions long. It happens in 2 microseconds, so it's not in that routine long. Switch the interrupts off and then switch them back on again at the end before you return. So it compares R8, which is the upper bit, the upper byte of the timer, with R16, and it compares R9, which is the greater byte of the timer, with R17, and that's a compare with carry. So it sets up the flags in the status register, and then when you go back again, you can do a branch on less than, or yeah, it's invariably a branch on less than, in fact, to decide whether it should go to the next one there, branch on less than. All right, I think that about covers the timer routine, which is by far the biggest and most complicated routine in the whole thing, but there's still a few other things to look at. So when it's got the number of button presses all arranged in memory with the number of numbers in location 100 and the numbers of the button presses in locations 101, 102, 103, etc. We then want to calculate, we want to take those decimal numbers and turn them into a 2-byte binary number, or hexadecimal number if you like, which can be put into two registers and counted down as the number of seconds that the timer should wait for. So when the programming is completed, we come down here to calculate timer period. Now on the slide, I give an example of how this is done. I think this is probably the easiest way to understand it. So here in location 100, we've got a 4. That's the number of numbers we're going to look at. And the numbers are 3600. And here's how it works. Remember that these numbers are all less than 9, or they're all from 0 to 9. So you could consider them as either hexadecimal or decimal. It doesn't really matter. But one way or another, you have to calculate them all into a 2-byte hexadecimal number. So first of all, we load the number of numbers into register 6. We set an index to location 101. Now, the index is actually carried in the X register itself because you load a number from X plus. So it loads from the correct register and then it automatically goes to the next one. But for the sake of this algorithm here, I've said we have an index because I'm going to increment that later on, the increment index. So we set an index to 101. We clear registers 10 and 11. And we call a subroutine to multiply registers 10 and 11 by 10. Now that seems a pretty daft thing to do when we've just cleared it. We know what the answer is going to be, but it's part of a loop. And there's going to be other numbers will get put into there. And this was just the easiest way to do that. So we clear our 10 and 11, we multiply it by 10, and that is a subroutine. The subroutine is over here. We load the indexed number into R5. Now the index, remember, we set at 101, so the index number is a 3. We load that into R5, into register 5. We increment the index, so it now points to 102. We add R5, which is the 3, to R10 and 11. So now R10 and 11 have 0003 in. We decrement R6. So it started off as a 4, but now we decrement it down to 3 because we've only got 3 numbers left to look at. We've already picked up the first one. We say, is R6 a 0? Well, no, it's not. It's a 3. So we call the subroutine to calculate R10, R11, which contains a 3, remember, and we multiply that by 10. Now, this is the subroutine that does that. The way that it works, it makes a copy, first of all, of R10 and R11 into another pair of registers. It multiplies R10 and 11 by 8 by shifting them serially left 3 times. So it contained a 0003, and we left shift it 3 times. That will multiply it by 8. However, we want to multiply it by 10, so that copy that we made into the other register pair, we multiply that by 2 by left shifting it once. Then we add the copy to R10 and 11, and now R10 and 11 contains what it contained originally, but multiplied by 10, and we return. So now we've got 30 in the registers. We load the index number, which is now pointing to 102. We load a 6 into register 5. We increment the index so as it points to location 103. We add R5 to R10 and 11, so that instead of 30, it now contains 36. We decrement R6, which goes from 3 down to 2. We say, is R6 a 0? And it's not, so we call the subroutine again. We've got a 36 in there. We multiply that by 10, and it's 360. But remember that this is all happening in hexadecimal. This is happening in binary. So the number in R10 and 11 is the binary representation of 360. And we run around this loop. We load a 0 in. We load it by 10, multiply it by 10. We load another 0 in, multiply it by 10, and we wind up with 3,600 in this register pair. And by that time, R6 is a 0. So we say, is it a 0? Say yes, and we return. So that's the end of the calculation. On the next slide, slide 11, there is a little illustration of how the calculation works. So these are using the numbers that were there. 3, then the 6 gets added in. When you multiply 3 by 10, it goes to 30. That's hex 1 easy. Then you add in 6, you've got hex 24. You add in a 0, but you multiply it by 10, so 0168, and it shows how the numbers work out. You can work through that yourself. So you can read through this yourself. There's nothing very complicated in it. There's R10 and 11. The routine to multiply them by 10 is called R11 R10 times 10. And the routine is here. It shifts R10 and 11 with a logical left shift, shifted once, and in case there is a carry gets carried out of R10, it rotates that into R11. So it effectively shifts the two of them one position to the left. It does it again, and it does it again. So that's shifted 3 times now, so that's multiplied by 8. Here's the copy being made. R16 into R11, and sorry, R11 into R16, and R10 into R17. So the copy is being made into R16 and R17, and eventually that gets multiplied by 2 here by shifting it, left shifting it once, and it gets added back into R10 and R11. Yeah, so fairly simple. It calculates this number into a 2-byte binary number, which it then wants to store into program memory. Back on slide 1, we started off by looking at the end of the timing sequence. The only reason for that was that we're going to put the chip to sleep, and interrupt 0 handler is used to wake the chip up again. So I looked at the end of the timing sequence just as a sort of preliminary to looking at the interrupt 0 handler. However, we never actually talked about the timing sequence itself. But it's pretty easy. I don't have a slide on it, but I'll show you where it is in the code. First of all, let me just say something about how it works. Right at the beginning of the code, there is a label target. Now, the compiler uses the label to generate an address, and we have data bytes written at that target, and there are 2 bytes, 003 Charlie. Now, hex 003 Charlie is decimal 60, and what it's doing is it's defining 60 seconds, which is the default count that the timer will use if you haven't programmed it yet. I suggest that you simply load this into Studio and single step through it. It's pretty simple stuff, and it'll be fairly self-explanatory. It starts off by setting the Z register to 001E, which is the address where that target is. Then we do an LPM into R18 and an LPM into R19. And LPM is load program memory, and it loads 1 byte. From there on, it simply starts counting down R18, R19. It counts them down as a pair, and when it gets right down to 0, then it switches the timer off. In the meantime, it's keeping an eye on the button, because you can push the button during the timing period. If you push it and hold it for 5 seconds, it will go into programming mode. Or if you push it and hold it just for a short while, it'll go beep to let you know that it's noticed that the button is pushed. And if you let it go after that, it'll cancel the timer. As I say, it's quite easy to step through this code, but the only reason that I brought it up really was to point out that program memory can be loaded into a register with LPM. However, writing to program memory is a whole nother ball game. Right, in order to write to flash, it's a fairly complicated business. You can't write a byte to flash. You have to write a page. So it starts off on the slide by saying, see the instruction set SPM store program memory. And there it is. It gives you a description of what it's doing. And then it gives an example of how it stores a page. And this was the example that I used as the basis for the routine that I wrote. It starts off by equating page size B equals page size times 2, and I did that in my program. There, right at the top of the program, equate page size B equals 2 times page size. Page size is defined in the dependency here. And it's 32, but beware, it is 32 bytes. That's why we define the new definition of page size B, which is 2 times page size. So because we're going to be storing 64 bytes, we're not going to be storing them as 32 words. So data written to flash memory must be written a page at a time. For the ATtiny 85, see its datasheet, paragraphs 20.4 and 20.7.4, programming the flash. So let's just have a look at that. So there we have the page size for this chip, the ATtiny 85. It has an 8K byte program memory size. The page size is 32 words, so 64 bytes. So for me, 2 bytes are reserved for the seconds count. Now remember, they're already initialized to 003 Charlie for 60 seconds, and initialized to, there we are. Calculate the point in flash where the bytes are to be put at the address of target. Calculate the address for the 64 kilobyte block divided by 64. You calculate the address for the 64 byte block for the beginning of the 64 byte block that contains the location that you want to write. So you do that by dividing by 64, which you do by right shifting 6 times, which automatically loses the remainder. And then you multiply it by 64 by left shifting 6 times. And that gives you the address of the base of the block. Then you copy that 64 byte page to RAM, and you do that with LPM, with load program memory, 64 times in a loop. You insert the 2 byte timer seconds count into the right position in the block in RAM. Then you clear the page in flash. You clear the page in program memory, and then you copy the 64 byte page from RAM to flash. It all sounds pretty complicated. And, well, yeah, it kind of is. It took some getting to grips with. The SPM instruction, store program memory, is what you use. And it does different things according to the bits in SPM CSR, which is paragraph 19.9.1 in the datasheet. So there's SPM CSR, it's this register, and it tells you what the bits in it are, and it defines each bit what they do. Page write is one of the things we're going to want to do. If this page is written to 1 at the same time as SPMN, the next SPM instruction within 4 clock cycles executes page write with the data stored in the temporary buffer. So you've got to get your data into RAM first. The page address is taken from the high part of the Z register, the Z pointer. The data in R1 and R0 are ignored. The page write bit will auto clear upon completion of the page write, so R1 and R0 get used to transfer that information from memory to program memory. The page erase is another operation we're going to want to do. That's bit 1 in the register. If this bit is written to 1 at the same time as SPMN, the next SPM instruction within 4 clock cycles executes page arrays. So it's all dependent on setting bits in here and then executing SPM within 4 clock cycles. Now the way that gets done in the program is by passing values in a register to do SPM. I've written a little explanation at the top here. The block in flash has been moved to RAM address. The offset for the period insertion has been calculated and is pointed to by the X register. X register points to RAM and the Y register points to flash. The block in flash is pointed to by the Z register. Move R11, R10 to the target address, and this of course is in RAM. So R11, R10, remember, is after the calculation we did. That calculated value is still left in R11, R10. So we use R22 for passing values to do SPM, down there, do SPM. So we load these two bits, which are defined in the definitions file, into R22, and we call do SPM, and it does it within 4 clock cycles. That's the whole reason for having this routine, and that is for the page arrays. Now we want to transfer bytes from RAM to the flash page buffer. So we could just have used R20 here because we're dealing with a relatively small page. On some of the bigger chips, I guess this page is much bigger and you require 2 registers. But never mind, the 2 registers were in the routine and I just copied them. So you load a value into R20 and you go into this loop here where you load R0 from X plus, which is pointing into RAM. Then you load R1 from X plus. So it's stepping through the RAM addresses, loading them into R0 and R1, 2 bytes at a time. Then we load R22. This is the one that's going to pass our bits to do SPM with the necessary bits. We call the do SPM and it writes those bytes into the page buffer for program memory. And that page buffer is somewhere inside the chip and it's concealed and I couldn't figure out how to display it or how to get at it. You've just got to, I think, take it on faith that it's there. So that's how this routine works, by writing these bytes into R22 and passing it down to the do SPM, and it does the business. Here's where the page write gets executed, and there again it's by loading the right bits into R22. There's the bits, and those are the bits that we saw on the datasheet there. It's the bits in this register, SPM CSR. Store program memory, control and status register. So we load the right bits into it and we call do SPM, and that writes the page into flash. So it's a bit of a complicated business, but once you've got a sort of template for the routine to do it, it's not too bad. It took me a lot of searching to find this template though. I searched a lot of websites and it was really quite difficult. That's why I'm really doing this course, to try and pass some of this knowledge on, because for anybody wanting to do this stuff, it really is hard to find. All right then, folks, I really think that we've about covered the course now. All right then, people, that's about it. We've got to the end of it. So if you've stuck with me until now, wow, congratulations on your tenacity. I really, really hope that you've learned something. I'd just like to point out that I'm not getting anything out of this at all. Let me just sort that out. I'm not registered with YouTube for profits, and even if I was, I wouldn't expect a programming course, an assembler programming course, to exactly go viral. So I wouldn't really make anything out of that anyway. I've put a lot of time and effort into this course. It's taken me about 3 weeks, working quite long days sometimes. So I really do hope that you've got something out of it. Now you can go ahead and do your own projects, and if you do anything really great that you really feel is worth sharing, share it with me. All the best then.